Hello, wonderful students. Dr. Mandis here talking about entropy. Entropy is part two of our thermodynamics series. Thermodynamics is the energy of systems. The last time we talked about enthalpy. Enthalpy was the energy to make and break bonds, basically. Entropy is basically organizational aspect. It's technically the measure of randomness or disorder, and that usually freaks out students a little bit until I just say, hey, it's just how much you got to pay, the energy you got to pay just to organize things. If you're going to bring two atoms together to bond, they have to come together, then bond. The bonding is enthalpy. The coming together is entropy. If you break a bond, that's enthalpy. If you move the particles away from each other after breaking the bond, that's entropy. So it's just how screwed up things are. Let's compare, and that's usually gets everything down. If you compare in these examples, water, solid versus liquid at the same temp, liquids rotate and vibrate, solids only vibrate. So the liquid should be more screwed up, more disorganized than the solid. So the liquid has more entropy. And the next one we have two solids, iron solid at 37 versus iron solid at 80. Well, 80 it's going to be moving faster than at 37 because remember temp is talking about how fast particles are going. So at 80 it's going to be moving faster. That's going to be more screwed up. That's going to be more entropy. In the next line I'm trying to introduce you to chemical reactions a little bit. We got hydrogen gas and carbon solid on the left, methane gas on the right. Well, you got three particles on the left, one particle on the right. Three particles is going to be more screwed up than one. Plus you have more gas phase particles on the left than on the right. So the left is definitely going to be more chaotic, have more entropy than the right. Next line, the dissolution of an ionic solid is kind of what I'm getting at. Don't be intimidated by that. I'm just saying, hey, you got an ionic compound, it's breaking up into ions. Which is going to be more chaotic? Well, the one with all the ions. Okay, but I'm also trying to show you here is that this is aqueous. Aqueous is going to have more motions than the solid. Just like liquids had more than solids, gases had more than liquids. Aqueous, if you dissolve something in aqueous solution, it moves around a lot more than as a solid phase. So typically aqueous beats out a solid for entropy. What we're doing here is something called positional entropy. It's just a qualitative comparison, kind of like when you have to line up by height. If you line up by height, you don't measure height, you just compare heights. We're just comparing entropies, we're not measuring them. Okay, here, the next phase, when we talk about the entropy of reaction, much like we did the enthalpy of reaction, we're doing this whole gig of the products minus the reactants, the final state minus the initial state. Now we're going to get into some numbers. All right, those numbers have units, and those units are right here. They're either going to be joule per Kelvin, depending upon if you cancel the mole out or not, or joules per mole Kelvin, which is more common. I have two examples here. One is just a comparison, and then the other one we're going to get to the numbers. And the first example, I'm going back to those exact same ones we did. If you did the water at 0 to 0, solid versus liquid, you're going smaller to bigger. So that's a gain in entropy. And so what I'm trying to stress is gains are positive, typically. You know, in the next line, we got iron at the lower temperature to iron at the higher temperature, 37 to 80. Well, that's again smaller to bigger, which is going to be a gain of entropy. Because if your money pile went smaller to bigger, or your weight went from smaller to bigger, those are gains. Gains are positive. Losses are negative, and we see the loss in the next line. Here, in the hydrogen gas with that carbon going to methane, we're going from bigger to smaller. That's a loss of entropy, and that's going to be a negative value. Alrighty, and magnesium chloride, and the next one is going back to a gain when we do that dissolution of the ionic solid, and so that's going to be a positive gain because we're going from smaller to bigger. That's a gain in entropy. You can either, sometimes you're asked to just qualitatively say, hey, is entropy going to be a gain or not? Because we want to say, is this reaction going to be favored in terms of entropy? You don't have to calculate it. You can just look at it. If entropy is going up, that's always favorable. If entropy is going down, not so much. That's an unfavorable reaction as far as entropy goes. In example two, we're just going to do the calculation. Students always screw up these calculations. I would say always. But on a test of like 20 students, I would say at least a quarter screw up the calculation. Not from lack of knowledge, from lack of being diligent with where they put numbers, where they put the units, how they put positives and negatives in, and stuff like that, because it just tends to be a lot of bookkeeping, and bookkeeping wigs students out on tests when they're all freaked out anyway, and so they tend to screw things up. So when you do these, just be slow and pedantic. Just be careful with what you write. Alrighty. Anyway, you're going to do the general equation, products minus reactants. Then we can plug in our products and our reactants. Pay attention, the n there in the first equation, the n refers to the coefficients. That's why we have a 1, a 3, and a 2. Don't forget, in these state functions, it really matters. If you double how much you get, you double the energy output. So the coefficients matter. When you sub them in here, the coefficients have units of mole. So we plug in the units of mole. These values here, if you have a textbook, you can get them from the appendix. If you're going online to find your numbers because you don't have the textbook, you can look at them online. Just make sure when you look things up that you know what they're talking about. Like when I looked up hydrogen gas to find it, the first thing that pops up is H atoms in the gas phase, not H2 diatomic hydrogen in the gas phase. So pay attention to the exact chemical formula if you look things up online. It's easier in a textbook because it's staring you in the face and so you see them. Anyway, you do the math here and you end up with a negative entropy. So this reaction would be a loss of entropy, which is what we predicted up here that we're having a loss. And so everything makes sense. If you look at the units, they're going to be joules per Kelvin because those moles all canceled out up above because mole canceled mole, mole canceled mole, mole canceled mole. Anyway, hope you learned a little bit about entropy right now. Learn it and like it, and I will definitely talk to you later.